We present a fully automatic method for stochastic inverse procedural modelling of tree models, that is, finding the generation parameters for a given geometry. In general, this is a complex problem. However, by restricting ourselves to branching structures, we have found an efficient approximate mechanism. Our method allows us to automatically convert existing tree models into a procedural representation of their species that can be used to create visually similar copies of the analysed trees. The input of our method involves 3D models from a wide variety of sources, created using tree modelling tools, grown virtually using biologically based systems, or reconstructed from 3D data. The obtained trees often look very realistic, but once they are created, the models are static. Using these models to assemble forest scenes produces unconvincing results of low visual quality. Each tree would have to be modelled manually according to its environment. One way to create many different trees interacting with their environment is to use a developmental model that simulates the tree growth. We use a developmental model that is controlled by a wide range of input parameters that control the growth process. By changing the parameters, our model allows us to generate a large variety of trees from different species. And it is easy to interpolate the tree models via their defining parameters. However, it is extremely difficult to manually select parameter values that would produce trees similar to the input. The aim of our approach is to automatically find a set of parameters that would generate stochastically similar output trees for a given input. We achieve this goal through optimization, traversing the parameter space and maximizing a similarity measure between the input tree and the trees generated by the developmental model. When the parameters are found, the input tree can be stochastically reproduced and even regrown in a new environment. The representation of the input tree by a set of parameters for a growth model is a very effective data compression of the input. This scene shows various trees that have been reproduced from XFrog models. Here is a similar scene, but only showing tree models that were reconstructed from laser-scanned point sets using Livni et al.'s method. The third scene only shows trees that have been grown using OpenL systems. Here we show an artificial scene filled with unique instances of the same tree species reconstructed from a single input model. The trees show visual variety, but still resemble the input. They also interact with each other and with obstacles in their environment. The input trees would need several gigabytes of memory space. However, in our representation, each tree requires only a few hundred bytes. Here is another scene, but filled with trees of various species that have also been generated using our approach.